Okay, welcome back. Right, so I wanted to draw these Cambrian lattices just to show what they look like. So I'll tell you that these are two different Cambrian lattices of type B3. So here, W is B3, which has Coxeter graph looking like this. So here's S0, S1, S2, and this edge is labeled by 4. And these are, well, actually I'm forgetting which is which. I think this is, yeah, so this is for the case where C is S0, S1, S2. And this is S0, S2, S1. So these are two different standard Coxeter elements of B3, and for each one you get some Cambrian lattice. This is what they look like. So yeah, I guess I don't really have anything to say about it other than, I don't know, they look cool. Okay, so those are Cambrian lattices. One sec. Right, so I guess I'll finish saying one thing that I wanted to mention about pop stack sorting, and then I will talk about this thing that I sent in an announcement on Canvas about basically, I think it was maybe problem 2 or something. Something that maybe I should not have expected to be done on the p-set, but I'll just explain the background, and I think it reduces the problem to just a question about acyclic orientations of graphs. And then after that, we'll go on and talk about root systems. So, okay, yeah, the one last thing I wanted to mention about pop stack sorting is, so remember, Cam sub C is this special set of C sortable elements of W under the weak order. So this forms some lattice, a sublattice. And the set of atoms, oh, so maybe I should say what an atom is. An atom of a poset is just an element, so if there's a unique minimal element of your poset, then an atom is just something that covers the unique minimal element. So I guess in these pictures, these are the atoms, 1, 2, 3, and in this picture, these are the atoms. So they're the elements that cover the bottom thing. And in a Cambrian lattice, the atoms are just going to be the simple reflections. So okay, I'll just say, i.e., elements covering 0. Are just the simple reflections. And this is because, well, the simple reflections are the atoms of the weak order, and they're also C-sortable. If you just think about the definition of C-sortable, it's sort of immediate that a simple reflection by itself is just going to be C-sortable. And one thing that I'll just state without proof is if you take one of these atoms, which is a simple reflection, it turns out that the set of elements of the C Cambrian lattice with the property that x is greater than or equal to s and x is not greater than or equal to any of the other atoms. So x is not greater than or equal to s prime for all s prime in S but not little s. So this is some subset, and this has a unique maximal element, which I'll call P sub s. So actually, I guess maybe there's a good thing about having these pictures because I can illustrate what this is doing. So if this is, oh, here's, yeah, chalk. Okay, so if I have this blue atom, I can look at the things that are greater than or equal to this atom, but not greater than or equal to either of these. So I guess that would be that element by itself, and maybe that's it. I think in this case that might be it. If I look at this, atom, then this element is greater than or equal to it, but not greater than or equal to either of the other atoms. And I think that those are the only two ones. And then the last one is this. And I think we can take this element, which is not greater than or equal to the yellow or the blue atom, and maybe this also. Yeah, that also works. And I think that's it. Right. So in this case, if this is S, this would be like, if this is S, this is p sub S. If this is my S, then this would be p sub S. And if this was my S, then this would be p sub S. And I guess I could also do this for this one. All right, blue, red, and yellow. And for blue, I think this is it. For yellow, maybe I also want to include this element, because that's bigger than this, but not those. And then I guess I can also do this one, but not that one, right? And then for the red, I think I can do this, and also this, and not that, so I think it's those, okay? So you can see that for each one of these colors, like the set of things of that color has a unique maximal element, which is the p sub S. So maybe I can make a remark.
What about that?
Oh, did I miss something? Which one?
The red.
The red, oh, this? Ah, yes, I did miss that, thank you. Yes. Okay, but I think that's it, right? Okay, cool, thanks. So, this is sort of just a side remark, but there's this area in representation theory called quiver representation theory. And basically you start with a directed graph that's called a quiver, and you sort of assign vector spaces to the vertices, and then you assign linear maps to the arrows in the quiver. And there's a way of interpreting the Cambrian lattices in this story. Basically, there's something called a tensor algebra, and from this you can define a lattice that is defined in this representation theoretic way. And the Cambrian lattices end up being isomorphic to these representation theoretic algebras, or lattices coming from the algebras. And these elements p sub S in this story correspond to projective modules. So in some way these elements are, okay, maybe I won't say what they are, but the point is that these p sub S's have like a nice representation theoretic interpretation, which is sort of why they're interesting. And so let me define theta, or theta sub c, let's say, to be the set of elements in the Cambrian lattice such that x is greater than or equal to p sub S for some S. For some atom S. So it's basically you take, well, I guess I can illustrate what it is here. So I would take these three p sub S things, and I would look at everything that's greater than or equal to them. So it would be like all of this. Okay, that's fine. I think that's theta sub c in this case. Right. And then over here, it would be this set. except maybe not this one. Maybe it should be in this. Oh, but also, not this one. I didn't plan this in advance, but, and also not that one. Okay, it's that, I think. Is that right? I think that looks right. Yes. Okay. So those are the theta sub c sets. And okay, so I'll just, oh, maybe here's a simpler example. So if I just take W to be S3, and I take C to be S1, S2, then K sub C looks like this. It's like a pentagon, where here this is the element S1, this is the element S2, which is also equal to P sub S2, and this is the element P sub S1. Right, so if I drew my picture with colors, then I would say, like, here's an atom, and this is the P sub S, and then here's another atom, which is its own P sub S. And so in this case, this theta sub C would be this stuff here. So I'll just mention one last theorem. So one reason I wanted to mention this theorem is that Yunso and Nathan in their paper made a conjecture about, like, a description of the image of pop on a bipartite type A Cambrian lattice. And this theorem resolves that, although it's like stated in this language. So it's not in terms of like permutations. But this is with Emily Barnard and me and Eric Hansen. I guess forthcoming. So an element of K sub C, or let me say an element W in K sub C is in the image of pop if and only if W is not in the set theta sub C, and the right descents of W all commute with each other. So I guess, like in this case, I'm looking for elements that are not in theta sub C, so these would be these two elements. And for both of those elements, the set of right descents, well, they all commute with each other. In this case, the right descent of S1 is just S1, which, I mean, it's just one element, so it commutes with itself. And then for the identity, it has no right descent, so sort of vacuously all of the descents commute with each other. So the image, in this case, is just these two elements, which you can check is actually the image. I guess for this it would be more complicated, but yeah, so anyway, I just wanted to mention that. Right. Any questions about this stuff? Oh, yeah, okay, so it's like representation theory. I feel like there should be maybe a way to prove it with like just lattice theory and Coxeter groups, but we didn't do that, and I haven't bothered doing that, I guess, but like the proof that we have written down is like representation theory that I don't fully understand. I mean, I'm getting there. I'm reading through it. Okay. Okay, so now let me shift gears and talk about this announcement that I made on Canvas. So let G be a graph. So an acyclic orientation of G is, well, basically you just assign a direction to all of the edges and you don't want any directed cycles to show up. So it's an orientation of the edges of G with no directed cycles. Yes?
So once you have them here, is it hard to enumerate?
Oh, like in type A, for example, I think you can, yeah, I mean, I guess the enumerative question is maybe separate. Like for this question about like the bipartite type A, we construct an explicit bijection with certain Motzkin paths. But yeah, like in other cases, I think, I don't know how you would get the enumeration from just this. Yeah, so I think it's not immediate from this. So, okay, if alpha is an acyclic orientation, then we can get a partial order on the set of vertices. I'll call it less than or equal to sub alpha on the set of vertices of the graph. And this is defined by saying u is less than or equal to sub alpha v if and only if there's some directed path from u to v. There is a directed path in alpha from u to v. So here's an example. Let's say I just take, well, actually, okay, let me do a sort of non-trivial example. Let's take this graph. Maybe I'll call the vertices u, v, w, x, y, and z. And I'm just going to orient the edges in some way so that I don't have any directed cycles. So I'll do that like this. I'll direct this edge from u to w. And here I'll direct this one from u to v. This one goes from v to x. This one will go from x to w, from y to w, from x to y, from y to z, and this one I'll orient from x to z. Okay? And you can check that, well, assuming I didn't make a mistake, there are no like cycles such that if you go around the cycle, like you're always going in the direction of the arrows. So this will give us a poset, and the poset looks like this. So we have u at the bottom, and this is because u is a source. So a source is just a vertex such that all of the edges incident to it are pointing away from it. And similarly, a sink is an element such that all of the edges incident to it are pointing toward it. So U is a source, here W is a sink, also Z is a sink. So the two arrows incident to Z are pointing toward it. So because U is a source, it will be a minimal element of this poset. So here's U, and I'll just write it down. There's V, X, W, Y, and Z. So the two maximal elements of the poset are W and Z, and that's because those are the two sinks in the acyclic orientation. Right, so for example, Y is V less than Y, well, I can draw a directed path from V to Y. I'll put a little diamond to represent that the example is over. Sort of like a square when the proof is over. Okay, so now let's go back and say that we have a Coxeter system. Where's my other chalk? So let WS be a Coxeter system with S finite. And let gamma be the Coxeter graph. Okay, so proposition. Oh, yes.
I was wondering why is it like y less than w and x?
Oh, maybe I made a mistake. Why isn't y less than w? Oh, it should be. Ah, good point. Yes, y should be less than w. So maybe it should be like this. Except I don't need this edge now.
But also doesn't like W, Y, and Z all cover X?
W, Y, and Z.
They're all like.
So Z actually doesn't cover X, and the reason is, even though there's an arrow from X to Z in the graph, in the acyclic orientation, you can go from X to Z in this like longer path. So in the poset world, this is like saying that X is less than Z, but, oh wait, yeah, but there's something between them, because you can draw, like X should be less than Y, and Y is less than Z. So I guess maybe what I'm doing here, when I draw the Hasse diagram, is I'm sort of deleting some of the edges that might be like redundant. Like I don't need this edge from X to Z to know that X is less than Z, because I know that I can go through Y. Something like that. Okay. Yes, thank you. Okay, so the proposition is that standard Coxeter elements of W correspond bijectively to acyclic orientations of the Coxeter graph. And then furthermore, the reduced words of a standard Coxeter element correspond to the linear extensions of the associated poset. Or I guess maybe I could say like, well, okay, so the standard, yeah, the reduced words of the standard Coxeter element corresponding to an acyclic orientation alpha are really just the linear extensions of this poset. Well, the elements of the poset are the elements of S, because those are the vertices of the Coxeter graph. And the partial order is this less than or equal to sub alpha. Maybe I should remind you what a linear extension is. I think one way that I phrased it on one of the P sets is it's like a bijection from the poset to the set of numbers from 1 to n, with the property that basically the numbers like increase. If you think of it as a labeling, they increase as you go up the poset. You could also just think of it as like listing out the elements of the poset with the property that you're sort of listing them going up. Or maybe a better, more precise way to say it is you're listing the elements of the poset so that at each step, whenever you write down one of the elements, it is not below any of the elements that you've already listed. So like in this example, there would be two linear extensions, which would be UVXY or UVXYZW. So let me do an example. Let's say W is S6. And so the Coxeter graph is just a path. So it looks something like this. So here's S1, S2, S3, S4, S5. And the I should orient it. So let's say I orient it this way. So I make that one go to the right, this one will go left, this one goes to the right, this one goes to the right. And so the associated poset here would look something like this. The sources are S1 and S3. So I have S1 and S3 at the bottom. S2 should be bigger than S1 and S3. And then I think I have this. This is S4. This is S5. I basically just taken the path and kind of made it look like this sort of, up-down kind of thing. Sort of like a mountain-shaped thing. So the Coxeter element associated to this would be, well, I could read off some linear extension of this. So for example, it could be S1, S3, S2, S4, S5. And you can check, maybe I didn't say how the correspondence goes. So the correspondence is where you say, for any edge in the Coxeter graph, I'm going to direct it away from the simple reflection that appears first in the ordering. So for example here, I have this edge between S2 and S3, and I say S3 appears first, so I'll direct the edge away from S3. Okay? And I guess as another example, if I look at the edge between S4 and S5, S4 appears before S5, so I direct the edge away from S4. But there are other words that I could have written down here that would have given me the same acyclic orientation. So for example, I could have written down S1, S3, S4, S2, S5. or S1, S3, S4, S5, S2, or S3, S1, S4, S5, S2, or S3, S1, S4, S2, S5, or I could have written S3, S1, S2, S4, S5. And I believe these are all of the reduced words for this element of the group. And you can see they're basically the linear extensions of this poset. So, right, like this linear extension is where I go S1, S3, S2, S4, S5, so I'm going up the poset. Similarly here I'm doing S1, S3, S4, S2, S5. So again, going up. And so there are 6 linear extensions of this poset, and they are just the reduced words of this Coxeter element. And maybe I should say that, well, you can see that these elements are the same, these words are representing the same element of the group, because I get from this one to this one by just swapping S2 and S4. But S2 and S4 commute, because we're in this, the symmetric group. They're not adjacent here. So I just swapped 2 things that commute, so I'm, it's giving me the same element. Same here, I just swapped S2 and S5, which commute. Here I swapped S1 and S3, which commute. Here I swapped S2 and S5, which commute, and here I swapped S2 and S4, which commute. Okay, maybe I want to erase this, but so here's the proof. If, let's say SI1 through SIN and SJ1 through SJN are 2 linear extensions, of this poset, then, well, I can get from one to the other by applying these Bender-Knuth involutions that I mentioned in a p-set. I think this is p-set 2. Right, so remember there was this thing where I said you have like a poset, and when you have, well, okay, I should say a linear extension when I phrased the p-set was like a bijection to the numbers from 1 to n. But here I'm thinking of a linear extension as just a listing of the elements that goes up the poset. And what the Bender-Knuth involution maybe I called it bk sub I. So what bk sub I does is it looks at the elements in positions I and I plus 1 in my list, and it tries to swap them. And it basically says, I will swap them if doing so results in another linear extension. So like here, if I tried to apply bk sub 2 to this linear extension, that would say I want to try to swap S3 and S4. But actually I'm not allowed to swap S3 and S4 because that would not give me a linear extension of this poset. So if I apply bk sub 2 to this thing, it actually does nothing. But really what these Bender-Knuth involutions are doing is, well, it's saying you're allowed to swap 2, like in this setting it's saying you're allowed to swap 2 consecutive elements if they commute with each other. That's essentially what's going on because, well, I'm allowed to swap 2 consecutive elements if they are incomparable in the poset. But it turns out that when you look at this poset, being incomparable will be the same as saying that there's not an edge between them. That essentially ends up being the same thing. So the point is, I can get from one to the other using Bender-Knuth involutions. Right, so this was the thing you proved in the p-set, and I think I mentioned that this is a good fact, and this is one reason it's a good fact. It's just like in many different settings. I wasn't actually planning, like when I made this p-set, I wasn't thinking that this would be in the solution, but then I realized like, oh yeah, this is like another place where this shows up. So in many different places, you want to show that you can get from one linear extension to another by doing these local moves. Okay, so I can get from one to the other using the Bender-Knuth involutions, and these just correspond to commutation moves. So this means that, well, I've gotten from this word to this word by just doing a bunch of commutation moves, so they represent the same element of the group. So thus, si1 dot 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 sin is equal to sj1 dot 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 sjn as elements of the group. Like they represent the same element. Right, so this is saying that two linear extensions will give me the same standard Coxeter element. But then I also want to say that if I have two words that are representing the same Coxeter element, then I want to say that they actually give rise to the same acyclic orientation. So conversely, if si1 dot 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 sin equals sj1 dot 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 sjn as elements of W, then we can use Matsumoto's theorem. So remember, Matsumoto's theorem says that you can get from one reduced word to another by applying braid moves. Maybe I guess the way that I phrased it was you can always get from any word to any other word using braid moves and nil moves, but in this case you don't have, or you're not going to use nil moves because these are both reduced. So actually you can get from one to the other using just these braid moves. So okay, let me say that. We can get from one to the other, like one of these words to the other, by applying, well, actually commutation moves. And the reason that you don't have any of these longer braid moves, things of the form like si plus 1 si equals si plus 1 si plus 1, is because in each of these words, well, I'm assuming that these are reduced words for a standard Coxeter element, so every simple reflection appears exactly once. So you're never going to have one of these longer braid moves because you don't have simple reflections appearing, multiple times. And so these are just braid moves, but you only have to look at the commutation moves. And then, well, these braid moves are really corresponding to the Bender-Knuth involutions. But the point is that they don't change the corresponding acyclic orientation. Right, like if you swap two elements, right? Like here, if I go from this one to this one by swapping the S2 and the S4, then that's not going to change any of the arrows here because there wasn't an arrow between S2 and S4 because they don't, because they commute. And then none of the other arrows get impacted by this. So these commutation moves do not affect the acyclic orientation. Okay. Oh, I stopped using my new convention. Okay. So there are these moves that you can do to an acyclic orientation, which are called source to sink moves and sink to source moves. And basically what this does is you take, well, a sink to source move takes a sink, like W here, and it turns it into a source by just reversing the orientations of all of the arrows that are incident to it. And you can check that if you have an acyclic orientation and you do a sink to source move, then the result will still be acyclic. You're not going to create a directed cycle by doing this. And then similarly, there's a source to sink move, which takes a source and turns it into a sink by reversing the arrows. So maybe I'll give an example of this. Well, I'll just draw that graph, I guess. So I could do, so let's say this is some sink. And I can turn this into a new acyclic orientation where I've turned this into a source by just reversing all of these arrows. And I keep everything else the same. So now this is a source. And a source to sink move is just going in the reverse, so I could do a source. Okay, so I could do a source to sink move to turn this acyclic orientation into that one. So if S is a source, of alpha, and let's say alpha is an acyclic orientation of our Coxeter graph, so S is some simple reflection, which is a source here, then the corresponding Coxeter element has a reduced word starting with S. This is just because when I draw the poset, S will be a minimal element, and I can find a linear extension that starts with that minimal element by just saying I'm going to start with this minimal element and then just find a linear extension of like everything else to complete the linear extension. Right, so I could just say, if I wanted to form a linear extension of this post-it starting with S3, I'll just write down S3, and then I'll just write down a linear extension of everything else, like S1, S4, S2, S5. And then if you perform a source to sink move, to S, well, this gives you some new acyclic orientation, which corresponds to a different Coxeter element, and that different Coxeter element is what you would get by just conjugating the original Coxeter element by C. So this just conjugates the associated Coxeter element by S. So here's an example. Again, W is S6, and I'll take this. Actually, I'm running out of white chalk, so let me do the yellow. Here's S1, S2, S3, S4, S5. Let's say I have this orientation like this. So this corresponds to the Coxeter element. Well, this is what I wrote down over here. So let me just pick one of these reduced words. Let's say S3, S1, S2, S4, S5. Now let me do a source to sink move on S3. So if I do a source to sink move on S3, I just reverse these two arrows that are incident to S3. Here's S1, S2, S3, S4, S5, and I've just reversed these. And now this corresponds to this Coxeter element. And this is just what you get by conjugating this one by S3. Because I multiplied S3 on the left to cancel this S3, and then I multiplied S3 on the right to add it back here. So a toric poset is basically just an equivalence class of acyclic orientations of a graph under these source to sink and sink to source moves. So a toric poset of a graph G is an equivalence class of acyclic orientations of G where two acyclic orientations are equivalent if one can be obtained from the other. Via source to sink and sink to source move. So I have a friend named Elise who's a grad student at University of Minnesota, and this is like the thing that she studies. So toric posets are cool. They have like interesting properties and you can do stuff with them. So I guess she's studying that for like her thesis stuff, and yeah, so they're cool. Let's see. So let me just state one last theorem here, which is maybe a motivation for studying these toric posets in the first place. There are other motivations coming from like geometry with hyperplane arrangements, but this is one motivation. So two Coxeter elements of a Coxeter group W are conjugate if and only if their corresponding acyclic orientations or maybe I should say two standard Coxeter elements if and only if their corresponding acyclic orientations of the Coxeter graph belong to the same toric poset. So one direction of this is something that I've already justified, because if they belong to the same toric poset, that means that you can get to from one to the other by doing the source to sink moves and sink to source moves that I just wrote down here. Right, like source to sink moves and sink to source moves correspond to conjugating by simple reflections that are either initial or final in this word. But then I guess the other thing is like actually, if you conjugate by any element, then this still preserves the toric poset. So in other words, toric posets of the graph correspond to conjugacy classes of Coxeter elements. And this only depends on like the underlying graph structure. This doesn't depend on what the labels of the graph are. So like if you looked at Bn, that's going to be the same as if you look at An, because Bn and An have the same underlying Coxeter graph, except there's a label of a 4 for Bn, but that doesn't matter when you're looking at acyclic orientations. Okay. Any questions about this? Okay, in that case, we can do geometric stuff now. I guess I've been alluding to this for quite a while. So, geometric representations. So as before, let WS be a Coxeter system. And we're going to let V be some vector space whose dimension is equal to the number of elements of S. So let me assume that, as I've been doing, I'll assume that S is finite. So V will be a vector space, and I'll pick some basis indexed by the simple reflections. So with basis, let's say alpha sub S for S in S. So I guess throughout this lecture I've been using alphas to refer to acyclic orientations. Now we're no longer talking about acyclic orientations. Now these alphas are basis elements of this vector space. So I'm going to define a bilinear form which I'll write like this. And probably I will forget to use a bar and I'll instead have a comma. This is what the book does, so I'll just keep this, but if I write a comma instead, you can correct me and tell me to write a bar. So this is a bilinear form on V, and we'll define it by letting alpha S bar alpha S prime equal the negative of the cosine of pi over this number m of s comma s prime, where again, this m of s comma s prime is the number in the definition of the Coxeter system. It's like the order of s times s prime. Okay? And so I've defined what this bilinear form does to the basis elements. And so by extending by linearity, or I guess by bilinearity, it's actually defined on the entire vector space.
Hold on.
Yes?
So, like, what are the entries of the vector space? Like, any number?
Like, I guess you can think of it as just real linear combinations of the alphas.
Okay.
So yeah. So just think of it as like, you've got these alpha sub s's, and you're just forming the vector space
Yeah.
with that as a basis. It's a real vector space. Yeah, maybe I should say real. Be a real vector space. That's actually important. So for each simple reflection S in S, I'm going to define a linear map sigma sub S from V to itself. And I'll define this by saying I want sigma sub S of a vector beta to be beta minus 2 times this bilinear form applied to alpha S and beta times alpha S. Okay, so the way that we're going to think about this is that we have this vector alpha sub S, and this is essentially like reflecting. This is going to be a reflection. And in fact, this is why these are called simple reflections. This is going to be a reflection basically through the hyperplane orthogonal to alpha sub S. Although we have to define it with respect to this bilinear form. I'll give an example of this, but let me just state some things about this. So this gives us a map sending S to this sigma sub S. And this map extends to a faithful is just a fancy word for injective here. A faithful representation of W. So all I mean by this is that, well, so I'll just say that is, if I take some element W, little w in my group, and I write it as a product of simple reflections SI1 through SIR, this means we can define sigma sub W to just be sigma sub S sub I1. Okay, so a lot of subscripts, but hopefully that's okay. Dot 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 sigma sub S sub IR. And this map is well defined. Maybe I'll say it's a well-defined injective group homomorphism. From the Coxeter group W to the general linear group GL of V, which is just the group of invertible linear transformations from V to itself. So the content of this, which I'm not going to prove, is that the way this is set up, the way that we've defined these sigma sub s's, is so that this map is actually well defined. If I took two different words representing W, and I defined sigma sub W using those different words, they would actually define the same linear transformation on V. And this is called the standard geometric representation. Of W. Okay, so let me work out an example. I guess, yeah, we have 10 minutes.
Sorry, what are the dimensions of each one?
What are the dimensions of what?
The spaces?
Well, there's only, I think, one space here, which is V, one vector space, and its dimension is the size is equal to the size of S.
Okay.
Should I do an example and maybe that helps?
Yeah.
Okay, so yeah, let's do this for S in. So here W will be S in. And so, okay, there I am defining V to be this vector space generated by the alpha sub S's. But actually, I think in terms of thinking about this concretely, it's helpful to let V be this vector space. It's going to be the set of all gamma 1 through gamma in R to the n, such that the sum of the coordinates is 0. So this is some n minus 1 dimensional vector space. And I'm just going to let EI be the standard basis vector in Rn. So EI is just 0, 0, 1, and a bunch of zeros, where this 1 is in position I. Right, so this is in Rn. Now, okay, the EI is not in this vector space because the sum of the coordinates here is not 0. But one thing that is in this vector space is I'm going to let alpha sub Si, so we're working in Sn, so the simple reflections are, our usual simple reflections of the symmetric group, and I'll define alpha sub Si, which actually I'm going to call alpha I just so that I don't have these double subscripts, which are kind of annoying. And this will just be EI minus EI plus 1. So now this is an element of this vector space V. And again, I'm sort of shifting perspective because over there I just said let V be the vector space generated by the alphas. Here I think it's helpful to be more concrete and just say let V be this vector space. But still the alphas are going to be a vector or a basis for this. Right, so we have n minus 1 of these alpha sub i's, and you can check that they do span this vector space V. They are a basis. Okay. So let's see what this bilinear form is doing. So first of all, alpha I bar alpha I is going to be negative cosine of pi over, well, I want to look at m of Si comma Si, which is just 1. Right, like in general, for any Coxeter group, it's always just 1. So this is negative cosine of pi over 1. Cosine of pi is negative 1, so this is 1. Now if I take alpha sub I bar alpha sub, let's say I plus or minus 1, so either alpha sub I plus 1 or alpha sub I minus 1, it's going to be the same thing because I'm going to take negative cosine of pi over, well now it's m of Si comma Si plus 1 or m of Si comma Si minus 1, they're the same thing, which is 3 in the symmetric group. Right, because the edge between Si and Si plus 1 is really labeled by 3 in this case. And cosine of pi over 3 is a half, so this is negative a half. And then also, if I do alpha I bar alpha j, where I and j differ by at least 2, then this should be negative cosine of pi over 2. And cosine of pi over 2 is 0, so this is 0. So if I apply, so I want to look at the sigma sub Si. What is this doing? Well, let's see what it does to the basis elements, these alphas. So sigma sub Si of alpha I is going to be, by this, this formula that I wrote down, it's going to be alpha I minus 2 times 1. So what's this? I'll just write it. Alpha I. But this is just alpha I minus 2 alpha I, so this is negative alpha I.
Really, this is alpha S sub I, right?
Yes, right, yeah. Alpha S sub I is the same as alpha I. Yeah.
Oh.
Yeah, I'm just doing a shorthand just so that I don't have.
I think maybe what I was confused about was we have infinitely many rules, right? Oh, wait,
Yes.
we don't.
Well, okay, I mean, actually, yes. You could write W as like S1, 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 S1 with a bunch, like an even number of S1s, and then just write down a word, and that will still be fine.
Okay, so I think maybe what I'm wondering is, in the case of S of n,
Mhm.
the cardinality of W is n factorial,
Mhm.
but then the dimension of GLB is n squared.
Yes. Well, yeah. Although, I mean, I wouldn't worry so much about the dimension of, or is it n squared? I mean, it's like that, right? I mean, yeah. Yes, yes, yes.
So like there's
But anyway.
some like linear combinations of words that give you.
Maybe I should say that like as elements of GL of V, these different sigma sub W's will not be linearly independent.
Yeah. Okay. So I
Yeah.
think maybe that was.
Yeah, right. Yeah, but I'm not really thinking of GL of V as like a vector space, I guess.
Okay.
Okay. So sigma sub Si just sends alpha I to negative alpha I. Let's see what it does to, so okay, what is sigma sub Si of alpha I plus 1? Well, this should be alpha I plus 1 minus 2 alpha I bar alpha I plus 1 alpha I. And, oh, maybe I should, let me just also point out that this is EI plus 1 minus EI. But what is this? Well, if you work this out, this is alpha I plus 1 plus alpha I, because this is negative a half. The bilinear form there is negative a half. And so this ends up being, well, so I'm doing EI minus EI plus 1. Sorry, no. EI plus 1 minus EI plus 2 plus EI minus EI plus 1. And that's just going to be EI minus EI plus 2. And so what I'll point out here is that really what we did in both of these situations is if we think of this vector in terms of its coordinates here, we swapped the ith and the I plus first coordinates. So here we had EI minus EI plus 1, we swapped the first, or the ith and the I plus first coordinates, and we get this. Here we had EI plus 1 minus EI plus 2, but if I swap the ith and the I plus first coordinates, the EI plus 1 becomes the EI. Okay? And I'm almost out of time, so let me maybe just write a little bit more. Sigma sub Si of alpha I minus 1 is alpha I minus 1 minus 2, so it's sort of the same thing. This is going to be alpha I minus 1 plus alpha I, and this is EI minus 1 minus EI plus 1. And if I and j differ by at least 2, if I take sigma sub Si of alpha j, this is alpha j minus 2 alpha j, alpha I. This is 0 now, so this is just alpha j. So in this case, it just fixes the alpha j. And maybe I'll return to this next time, but I'll just say, in general, what you're really going to do with sigma sub w, if w is an element of the symmetric group, is it's going to permute the coordinates of the vector in the same way that you would hope, right? Like w is actually a permutation, so it's just going to permute the coordinates in the same way that the permutation permutes numbers. Okay, so I think that's all for today.
So do you ever use that to show two representation of the words are different? So are they same or different? Isn't that they define as the same?
So you want to show that two elements define the same like two words represent the same element of the group, and so maybe you use like you show that they give the same sigmas.
Yeah.
Yeah, I think you could do that. Yeah.